So good afternoon, everybody, and welcome to the presentation. My name is Saurabh Karwal. I'm a business developer at TNO, the Netherlands. And today I'm going to talk about addressing the gaps in large-scale implementation of quantum devices. So before I delve into the topic of quantum activities at TNO, I'll first like to briefly introduce what TNO is, since this is my first time that I'm talking at Q2B. There are many research organizations in Europe. We call them RTOs, such as VTT, CLAT, Fraunhofer, and IMEC, and TNO is one of them. The main task of an RTO is to upskill the technology from an academic level to an industrial level. So we kind of form the bridge between academia and industry. Within Netherlands, we are located in many locations. We have a broad patent portfolio of almost about 1,000 patents. We are involved in 1,000 public-private partnerships, as well as we are close to 5,000 employees now. Now coming to profile and units of TNO, TNO stands for Netherlands Organization for Applied Scientific Research. That was established in 1932 by the so-called TNO Act. We are trusted advisor to the government. We have 6 units at TNO. I'm coming from the high-tech industry unit. TNO is also a non-profit organization, which means that we independently help companies innovate. So, we are helping companies, startups, scale-ups, SMEs, or big tech even, to overcome the valley of death. So TNO is operating anywhere between TRL level 2 to TRL level 7. Low TRL level is quite obvious, of course, but then we are also working at higher TRL level with big tech companies such as, for example, ASML and Carl Zeiss, where we are trying to help them with improving the optics lifetime of EUV mirrors so that they can withstand harsh EUV climate. TNO operates in different models. One is public-private partnership, where we are setting up joint innovation centers, and we are part of European projects where the funding is mix of public and private. The other one is contract research. So companies give us tasks, research and development tasks, which we carry them out and which is fully paid by the customer, as well as TNO acts as national lab for the Dutch government, where we get specialized tasks from Dutch government on specific topics. Now, coming to strategic collaborations and spin-offs, we are involved in setting up joint innovation centers, which I have already elucidated, meaning that those innovation centers are kind of focused towards developing critical knowledge. QTech is one example of that in the Netherlands, which was a joint venture between TNO and TU Delft to develop scalable prototypes of quantum computer and quantum internet, which is a low TRL topic, but then TNO is helping with engineering expertise to increase the TRL level to a higher TRL level. We are also involved in creating spin-offs to generate economic impact from research. We have broad portfolio of spin-offs as well. I'm just showing a few of them here. Orange Quantum Systems and near-field instruments are a spin-off of TNO, whereas companies like Quantware, QBlocks, and QBird are a spin-off of QTech. Now, coming to the quantum activities at TNO, which actually occurs or spread out throughout 3 units. We are hardware-driven people from high-tech industry unit, where we are working on quantum devices, materials, quantum computing, quantum communications, and quantum sensing. Whereas the defense unit that we have is working with Ministry of Defense on quantum sensing and quantum networks. The ISP unit that we have is working on quantum applications and algorithms, and Quantum Application Lab is one example of that. They are also working on ecosystem development and strategy consulting, as well as quantum networks and post-quantum cryptography. Now, when you look at the high-tech industry unit at TNO who is working on quantum, we are a workforce of almost 70 FTEs now, which bring in different competencies, of course. We have material and device fabrication engineers. We have device design engineers. We have engineers who are doing the device characterization and testing, as well as system integrators. In terms of facilities, we have 2 clean rooms in Delft. One is CMOS-based, and the other one is a hybrid between academic-style clean room, but also having high reproduction lines as well. In terms of quantum computing lab, we have Quantum Spire and KIT, which I will talk about in the coming slides, quantum internet lab and quantum sensing lab as well. Now, coming to the topic of discussion today, challenges in large-scale implementation of devices. Well, what I show you here is basically a 2-spin qubit chip, which is located in the mixing chamber at the bottom of dilution refrigerator. And on the right, what I show you is basically different layers that goes into full stack quantum computer. In this presentation, I'll be mostly talking about the lower level stack or the physical layer, basically, but we are also working on full stack integration as well. Now, what I've done in this slide is basically to list down a few of the challenges that prohibit large-scale implementation of devices, such as quality of quantum chip, the materials that we use, the interfacial defects, for example, which influence your qubit performance, the scalability, where you design your chips in a way that can scale, addressability, which means that you can address single qubit in multi-qubit operations, so thereby minimizing the crosstalk, measurement standardization, stack integration, etc. Some of the challenges we are working on at TNO to address them in different projects that we are currently working on, whereas some of the challenges we rely on our partners, such as Q-Blocks on control electronics. Now, I would like to switch gears and talk about a kit facility that we have, which is kind of the enabler that we have that addresses these challenges in various B2B and European projects. So this kit facility was actually opened in 2020, which was an open testbed facility with the main goal of helping Dutch and European quantum ecosystem with their R&D efforts. This facility has both internal and totally external projects as well. And in this facility, we have a range of capabilities and competencies, which is still expanding. So we have 2 dilution refrigerators where we can measure up to 20 transfer and spin qubits. We are procuring one more dilution refrigerator, which will enable us to measure up to 36 qubits. Then we have 1 Kelvin system, which is geared towards high throughput screening of quantum devices. We have 4 Kelvin system focused on material and defect characterization, as well as we are trying to procure a room temperature system, which will enable us to measure devices at a large scale or wafer level device screening as well. Now, coming to the European projects that we are part of, which are like very big projects with a lot of funding available, where KIT plays actually a key role. We are part of QTest, QPilot, Arctic, and QLSA 1 and 2. These projects actually enable us to develop critical knowledge in the field and also upgrade our facilities as well, so that we can actually, in the end of the day, we can actually help potential future customers and also current customers with the capabilities that we have. And these also allow us to connect with different RTOs and industrial players within Europe, as well as allow us to stay at the cutting edge of quantum research. So what I will do in this presentation is that I'll go one by one through each of these European projects, just to briefly talk about them. But if you're interested, please come and talk to us at QDNL booth. So in QTest, QPilot, the main aim of this project was to develop distributed infra within Europe for device screening and device characterization, and also device fabrication. So within QPilot, TNO is leading the quantum device development for Diamond program for feeding into quantum sensing and quantum communication roadmap, whereas in QTest, TNO is leading the quantum computing and quantum sensing roadmap to be able to measure qubits in a standardized way. So in this presentation, I'll mostly talk about the QTest program, where we are working on 3 topics. Superconducting qubits, which focuses on, it can be transmon or fluxonium, spin qubits, and traveling wave parameter amplifiers 2-pass. And the goal of QTest is to develop standardized European protocols to be able to harmonize testing protocols throughout Europe, as well as upgrade hardware and software that we have so that we can actually measure up to 20 qubits and then 36 qubits in future, and then also introduce automation and multiplexing so that we can reduce the measurement time by 50%. The other project that we are involved in is Arctic, which is, again, a huge European project with many partners. The main goal of Arctic is to have high-throughput device screening and component testing, which has different work packages. Within this, we are using 1 Kelvin and 4 Kelvin system that we have. So in this presentation, I'll mostly talk about few work packages. So starting with the couple of first work packages, which is focused or geared towards high-throughput screening of devices and components. So on the left, what you see is that we get spin qubit devices from TNO and Semyon. We get control hardware from Q-Blocks. We get control locks provides us with the control software where we can measure devices in an automated fashion, and TNO is integrating everything into one stack. whereas on the right, what you see is that the LNAs, low noise amplifiers, are provided us by VTT and ST microelectronics. Qblux is providing us with the RF modules, and TNO is developing the S parameter characterization and also noise characterization protocols and integrating everything into one stack. On our other work package, we are working on improving the spin qubit devices. So what we see often is that when we input a lot of microwave power, the qubit frequency shift occurs. So we are trying to understand where that is coming from. So we are working with IMEC on understanding metal resistivity. We are working with PicoSun on developing recipes for deposition of dielectrics with minimal defect incorporation. And we are working with Tyndall or Semyon on gate oxide, where we can characterize the defect densities at the interface between dielectric and silicon, as well as within gate oxide. And everything put together, the data that is generated is then fed into device modeling so that we can make our device or improve our device modeling further. Now, the last European project that I want to talk about is QLSA 1 and 2, which has the main aim of developing scalable prototypes of spin-based quantum computation. So spin qubit is based on two material platforms, silicon germanium material stack that we get from QTech, which is one of the largest and best performing qubit array to date, as well as FDSR wafer that we get from CLAT. And the goal of QLSA 1 was to demonstrate 8 spin qubit processor, which can be later integrated into full stack quantum computer. And TNO was doing QPU design, fabrication, device screening, as well as upgrading the setup for automated device tuning, as well as developing lower level stack. In QLSI 2, we have the same goal, but then going towards larger qubit arrays. So just to give you a brief example of how device development at TNO happens, that we are trying to close the loop between device design by simulations, device fabrication, and device testing and screening. So just using spin qubit as an example, but that can be also extrapolated to, for example, 2-power devices, where we start from the material growth, which we get from university. We do optical lithography to define hall bars, where we can actually measure the mobility density curves. Then if everything looks good, we do the E-beam lithography to define quantum dot devices. Then we do device screening, and if everything looks good, we load the device into condensed wire fridge. So this is also a good segue to actually talk briefly about Quantum Spire as well. So Quantum Spire is actually Europeans' first quantum computing cloud that was fully designed and engineered by TNO. It is a hybrid system which had 2 spin qubits and 7 transmon qubits in the past, but now we are trying to upgrade it towards going towards 8 spin qubit and 17 transmon qubits. And I think it's good to mention here that the transmon qubits that we are getting is actually coming from Leo DiCarlo's group at the university. All right, so this brings me to the end of my talk. We are looking for collaborations, of course. So Delft is a very good place to be in if you're working in quantum research. In general, we have certain propositions which I have already elucidated during my talk. So if you're interested, please get connected to us now. We'll be located at the Quantum Delta NL booth. So with this, I would like to thank you for your attention.